Hello everyone. Thank you very much for checking this video out. I'm a professor in the Department of Mechanical Engineering at Virginia Tech. The purpose of this video clip is to explore the role of chemistry in fluid dynamics. So fluid dynamics is a discipline that studies the motion of fluids as well as the interaction of the fluid flow with the surrounding. Fluid dynamics is everywhere in our life, and in fact, for example, hurricane is basically a classical fluid dynamics problem. And if you threw an olive into a cup of cocktail, then you see this beautiful splash, and that is also a classical fluid dynamics problem. And even if we just breathe, then we actually inject a jet into the surrounding air, and that is another classical problem in fluid dynamics. So fluid dynamics can be very useful. For example, design engineers can study the airflow near a speeding car, and that can help us to decrease the drag experienced by the race car, and hence we can make it go even faster. And fluid dynamics can be just also purely fun. For example, we could study the air flows near a running dinosaur and envision how much drag this monster actually could experience at the top speed. And if we have a cup of afternoon tea, we could also wonder what would the flow near a slice of cake if we have a gentle breeze brushing our cake. So by and large, fluid dynamics has been studied and practiced for thousands of years. And most of the time, we focus on microscopic behavior. And it's fair to say that the classic fluid dynamics say neither individual molecules or their interactions. And this can be appreciated by looking at the governing equation of fluid flow, which is the Navier-Stokes equation. So here we show a Navier-Stokes equation for a classic Newtonian fluid. And on the left-hand side, we see the mass time acceleration term. And on the right-hand side, we see the various forces responsible for driving a flow. So now the key thing that you can observe from this equation is that the nature of the fluid actually are entirely encapsulated in two numbers. One is density and the second is viscosity. So here we really don't see any individual molecules as well as interactions between these molecules. They are all hidden, packed, or encapsulated in these two very simple numbers. This is in stark contrast to chemistry. So in chemistry, most of the time or a lot of times, we are very interested in molecules, right? So how atoms are bonded to each other, and how if we have one molecule here, say for example, a lithium ion that is chelated by a very complicated molecule like this, right? So how their electron cloud actually will interact. So hence, really one key element or key aspect of chemistry that we really oftentimes are looking at individual molecules, their bonding, their interactions, and we care about specificity. And that is, if we have molecule A and we have molecule B, the shape and the size and how atoms are arranged make a great deal. And chemists are very obsessed in studying this kind of thing. And this is actually can also be appreciated by looking at the fundamental equation in chemistry, and that is the Schrödinger equation. So in this equation, both the wave function as well as the Hamiltonian are mostly, right, so people solve them or define them, explore them at a subatomic scale, right? And so here, really, the focus is a lot of time. It's at the kind of the atomic level, right? So here, things are very much oriented towards single molecules, or a lot of time. So now we say that on one side we have fluid dynamics where we really don't see individual molecules or we don't care about their interactions as long as we get our density or viscosity correct. Well, on the other side, we have chemistry that is relentlessly focusing on molecules and even smaller electrons. So it's fair to say that fluid dynamics has been largely separated from chemistry in the past. So this actually have served us very well. For example, a design engineer, when he try to optimize the flow near a race car so that we can reduce the drag, right? He or she does not have to worry about the size and shape of the oxygen and the nitrogen molecule, and even less so about, say, for example, the vibration of the atomic bonds. So, however, in the past decade or so, a lot of progress has been made in engineering practice that has significantly pushed the envelope of fluid dynamics. And this actually has forced us to take a look at the traditional paradigm where fluid dynamics is segregated from the chemistry. So in a series of videos, we would like to explore the role of chemistry in fluid dynamics. In this video, we explore the role of chemistry in CO2 sequestration. So CO2 is now recognized as a key contributor to the global warming, and there is a strong desire to store the CO2 released during combustion instead of sending them into the atmosphere. Many technology has been developed, and among these technologies, one of them is actually attracting particular attention, and this technology is shown here as a schematic. So the basic idea is that after CO2 is generated through combustion, instead of releasing them into the air, we capture them and then we inject them at high pressure into a so-called shell formation. So this way we can store the CO2 inside the formation. So now cell formations are quite famous nowadays, and it is well known that some cell formations actually hold enormous amount of hydrocarbons such as oil and gas. So in this case, right, so if we store CO2 in a cell formation, and at the same time we may be able to actually use this CO2 to enhance the recovery of either oil and gas from the reservoir, and that could be a really good idea. So now, before we can use this technology effectively, we must first understand some basic features of cells. So now cells really are some, rather unique rocks. First of all, compared to the common rocks, they have much more higher populations of nanopools. Shown on the figure on the left here is the pool size distribution of a typical shell rock. We can see that the pool size actually really has a significant fraction of them. Between 1 to 10 nanometer, actually they occupy a significant amount of pool space in the rock. And another aspect of shells that are very special is their physical and chemical heterogeneity. Shown on the right figure here is the cross-section view of a cell sample. So we see that here we can see organic kerogen materials and also clays and sometimes quartz and calcite. And this material exists sometimes form pools, and the walls of the pools actually can be made of very different materials, and these pools can have different shape and different size. So overall, we say that the shells are really a very multi-scale, heterogeneous porous media, and the size of this pool are sometimes comparable to the size of a single molecule. Because of this, we can expect that the molecular nature, or more specifically the chemical details of the molecule, could start affect the transport or the flow of CO2 and oil inside the cell's nanopools. Although these are out of the scope of traditional fluid dynamics, and they are actually practically important. Because of this, we have performed molecular dynamic simulations of carbon dioxide flow into a single nanopool originally filled with oil. So shown here is a schematic of our simulation system. Our system are made of a calcite nanopool with a width of 4 nanometer, and the nanopool is originally filled with a highly pressurized oil, as in practical systems. On the right-hand side is a very large reservoir of CO2, and this mimics the CO2 injected into the cell formation. So now, initially, these two are separated by a single layer of plate so that to separate them. So now, although this is a very simple model, and it's much simpler than what you could find in practice, but the model does capture, right? So some essential aspect of the problem. First of all, the calcite nanopool actually are resolved at the molecular level. So in other words, the chemical details of calcite is taken into account. And also the oil and the CO2 molecules are also resolved at the molecular scale. So what that means is their chemical nature is also described with some fidelity. So together this positions us to claim that, well, some level of chemistry has been incorporated in our model. So once we build the model, we first equilibrate the oil and the CO2, right, with these two green plate fixed. Then at time equals to 0, we remove the plate that is near the mouth of the calcite nanopool. So now let's see what is going to happen. So in this case, we say that CO2 will rush into the pool. And interestingly, we say that some of this CO2 molecule get absorbed onto the surface and they display the decay molecule from that. And this is especially clear at the front of the diffusion. So this result now suggests, right, so an essential picture here is that as the oil flow into this, right, so we can see these two populations. One is absorbed on the wall, and this other is in the middle. So now the molecules absorbed on the wall can also displace a decay molecule originally there. And this way we can accomplish CO2 storage and also oil displacement, which is very useful. So now this absorption of CO2 molecules and displacement of decay can also be seen very clearly on the figure shown here. So what we show here on the x-axis is the distance from the lower channel wall, and the y-axis is the density. And we are showing the density of carbon dioxide as red and the density of decay as dashed line. And we can say that the CO2 molecule essentially displaced all the decay molecule from the first layer. So now you might ask why this is so. Well, this turns out to be completely governed by the chemistry of oil, CO2, and the calcite wall. So in our simulations, we use a calcite surface, right? So calcite, because of the peculiar chemical bonding between the calcium, carbon, and oxygen atom, as well as the different electronegativity of this atom. It so happens that the calcite and the carbon atom are both positively charged, and the oxygen atom is negatively charged. So now when a decay molecule, an oil molecule approaches, remember the decay molecule is actually an apolar molecule, and none of its atoms carry a significant charge. So because of this, affinity of decay to the calcite is entirely governed by the van der Waals forces, which is fairly weak. So now when we have a CO2 molecule, situation is quite different. CO2 is also a polar molecule. However, because of the different electronegativity between carbon and oxygen, so the carbon is positively charged and oxygen atoms are negatively charged. So when a carbon dioxide molecule approaches a calcite surface, what it does is it will systematically try to find the calcite and carbon atom, with which it actually can interact very strongly through the oxygen atom. And remember, the carbon atom is a little bit further away from this positively charged site. And because of this, the electrostatic interaction really drives the CO2 absorption. And because electrostatic interactions are much stronger compared to van der Waals interactions, so the CO2 molecules can outcompete the decay for the surface area of calcite. And this leads to absorption of CO2 on the surface and displacement of decay from the wall. So now the displacement of the decay from the wall as well as absorption of the CO2 on the surface actually can greatly contribute to the CO2 transport. And so in the figure below, we are going to study the evolution of the density along the axis of a pool, right? So we average the density at each of these cross sections and check their evolution. So that basically, is how, our x-axis is the distance from the pool mouth, and our y-axis is the surface density, or the density of absorbed CO2, and the density of the middle CO2. So that's basically what you can see. So what we say is that the blue curves, right, correspond to the dissolved CO2, right? So their transport contributes significantly to the overall CO2 transport, while the box CO2, right, so they lag quite a bit behind. So ultimately, right, so this different transport of surface dissolved and box CO2 lead to very different storage of the CO2, right? So the CO2 is stored inside nanopool as two populations. One is on the wall, and the other is in the middle part. So now the relative importance of the adsorbed versus the box CO2 can be characterized using the so-called storage factor we defined here. So in this figure, we showed how the storage factor changes as a function of the box CO2 density in different pools. This different line corresponds to different pools. So now we see, so this factor essentially is the storage by adsorption, right? So it's shown on these two blocks here, divided by the storage by adsorption in the middle part of the pool. So what this figure tells us is that inside a given pool, right? So as the density of CO2, box CO2 decreases, the storage by surface adsorption became more important. And as a given surface, a given box density, right? So as the pool became smaller, the adsorption contributed more to the storage. So basically, we claim that, surface storage really can dominate CO2 storage when the pool is narrow or when the box CO2 density is very low. So overall, our study suggested that because of the different chemical details of carbon dioxide molecule and the oil molecule, they show very different affinity to the calcite wall that we studied here. And this lead to rather different flow behavior of the CO2 as two populations inside the pool and the total storage mode of these two different forms of CO2. So none of these effects are considered in the classic fluid dynamics, but they are practically important for CO2 sequestration. So if you are interested in further details, please refer to this paper published in 2021.